One of the most interesting propulsion technologies that is actually being used today is the ion engine. And this is where you take some kind of inert gas, ionize it, and then fire it out the back of your spacecraft with electricity. And this is incredibly efficient. You can have these ion thrusters firing for days, months, even years, and generate enormous changes in velocity. Now, they don't have very high thrust, but they're very efficient. And so just with a few kilograms of fuel, you can actually go incredible distances at high velocities. But what if you didn't need to carry this propellant? What if instead you could just suck your propellant in from space and then ionize it and accelerate out the back of your spacecraft using electricity? You wouldn't need any fuel on board at all. And this is an idea that a lot of people have been investigating. It's called an air-breathing ion engine. And the idea is that you have a spacecraft at a very low altitude orbiting around the Earth, maybe 200 kilometers. It is drawing in particles of air, and then it is ionizing them and then firing out the back using the electricity from solar panels. And in theory, you then never have to refuel this. It's walking this knife edge between using thrust to maintain its orbit and deorbiting because of the drag that it's hitting from the atmosphere. It's a really cool idea, and it has the potential to solve a lot of problems in satellites. So my guest today is Dr. Mansur Tisaev, and he's a postgraduate researcher at the University of Surrey, and he did his doctorate on air-breathing ion engines. And this is an interview that I've wanted to do for a long time, and I finally found somebody who was able to talk about this, and it's a fantastic interview. Really goes into the details, and you really get a sense of where we stand in the development of this really revolutionary technology in my mind. All right, enjoy this interview. So people are very familiar with ion engines in general, or at least they're familiar with the missions that have ion engines. But I think, we're going to spend a lot of time talking about ion engines today. So can you give me sort of soup to nuts, how does an ion engine work?
How an ion engine works. Okay, so we've got two main approaches for propulsion once you're in space, on board your spacecraft or on board your satellite. So that's chemical or electric, which people often refer to as plasma thrusters or as ion thrusters, like you've just said. So chemical, I think that's more well known to people. You react a gas or you heat it, and that's thermodynamic expansion. So you throw the gas out of your spacecraft and that pushes you the other way. With electric propulsion or ion thrusters, you're electromagnetically accelerating individual ions. So what you want to do, you want to take a gas and you want to split it into ions and electrons. That creates a plasma. So once you have this plasma, you can then use electromagnetic forces to accelerate the ions. And it's the same concept of a net transfer of momentum, because the ions are leaving your spacecraft at high velocity, and so you gain thrust that way. So kind of in broad terms, chemical thrusters produce a high level of thrust, but they're not so fuel efficient. So you run out of your propellant quite quickly, or you have to take quite a lot of propellant with you, but you can go a long way. Electric thrusters or ion thrusters, the advantage is a much higher fuel efficiency. So you can, a certain amount of propellant lasts you a lot longer. You can station keep for a really long time, or you can go really far in the solar system. But the disadvantage is that the thrust level is very low. So like the common one used is like, it's enough to lift a piece of paper, like overcome the gravity of a piece of paper on Earth. So that's kind of the overview.
And I mean, we've seen ion engines used in several NASA missions, Japanese missions. The Starlinks are using ion engines for their station keeping. Even more powerful versions are being developed for potentially station keeping for the Deep Space Gateway. So there's a lot of applications of ion engines. So now, what is an air-breathing ion engine?
Yeah, also just to add to your point, a really cool mission is the European Space Agency Bepi Colombo mission to Mercury. So, and I'll give a shout out to that as a European.
Yep.
So air breathing specifically is kind of like one of these exciting new areas in electric propulsion in ion engines, and that's like people thinking basically, can we fly in very low Earth orbit in the upper reaches of the atmosphere where there's still actually some residual air? It's very, very rarefied, like very low density, but it's enough to basically take that air and collect it as propellant for your thruster. So you wouldn't have to take any propellant, any fuel with you. Often ion thrusters use xenon, for instance, because it's quite nice for a number of reasons. So you wouldn't need to take any of that with you, and the life of your spacecraft, how long you're able to use your engine for, isn't limited by propellant from Earth. So you're basically flying through the propellant you're using. And normally in these very low Earth orbits, so we're talking about 200 kilometers altitude, this kind of range, about halfway to the International Space Station, which is at about 450 kilometers. Basically, you normally encounter high levels of drag, which will bring your spacecraft down. So being able to produce thrust to counteract this drag would mean that you can stay in these orbits, without basically re-entering. It's kind of a nice, very high efficiency way of using your spacecraft. And if I may, one final advantage is that increasingly now space debris is more and more of a problem. So in these orbits, that's a nice advantage that you wouldn't leave any space debris, because as soon as your spacecraft stops working, it will re-enter in a couple of weeks.
Well, I think there's a bunch of other advantages as well that I would like to get into kind of later on in this conversation. But so, I mean, this is the trick, right? Is that you're experiencing drag on your spacecraft, which is trying to make your spacecraft re-enter. But at the same time, that thing that you're experiencing drag from is a potential propellant. You've got unlimited energy coming from the sun to power up your systems. So the question really is, can you get enough of this propellant? Can you counteract that force? So talk to me about sort of I don't know, I'm trying to think. It's like a balancing act, right? And was it even
exactly.
People weren't even sure this would be possible, because it might be that, no, actually the drag is too much. You're not going to be able to get enough. But where are we on this side of this balancing act?
Yes, it's a little bit on a knife edge, and you actually do a very good job of describing it. What it ends up being is quite a coupled problem, if that makes sense. It's quite circular, because basically the thing that is creating your drag is also the fuel source. So it's not really about how much thrust you can generate, which is a little counterintuitive. It's not about how powerful your engine is. It's about how efficiently it operates. So how efficiently can it take this air and accelerate it, ionize it into plasma and then accelerate it to create thrust, versus how much drag the ingestion of this air actually takes. So this is something I started working on in my PhD for the first part of it. And you see kind of increasingly more and more research about this in the field at the moment, this kind of mission analysis aspect, like where can we fly and where is it actually possible to counteract drag? So this then brings you on to more kind of what type of propulsion system do you need? Like, does it need to prioritize specific impulse, which is related to kind of, it's like a measure of fuel efficiency related to sort of how fast you're accelerating ions? Or should you prioritize sort of thrust to power, right? Like how big do your solar arrays need to be in order to generate a certain amount of power for your thruster? Sort of your power efficiency of the engine. Because obviously the bigger your spacecraft is, the bigger your solar panels are, the more drag you generate, which I think this is kind of like a bit of a new problem for spacecraft, right? Usually it's like, well, you launch into low Earth orbit or higher, and you don't really have to worry about drag. You don't have to worry so much about how your spacecraft looks like. It's more maybe for thermal reasons or, these sort of priorities. This is almost like a fun challenge to bring it more into the aerospace domain. So yeah, some aspects of like the aerodynamic shape of your spacecraft actually are becoming more important in this kind of problem.
And I guess also the collection area, like your intake for your air. I mean, it's making a spacecraft that looks more like a whale shark as opposed to, a more, I guess people don't really care what satellites look like as long as they get their job done. But as you said, now they have to start looking a little more aerodynamic and be able to draw that air in. And so
yeah.
What are you finding when you have that balance between intake for the oxygen, the specific impulse that you're trying to fire your propellant out at, the amount of power that you're trying to generate with your solar panels, when all of these variables come together, is it leading to you towards an optimal solution?
Yeah, it's starting to, and I think this is very exciting. Like at the moment in the field, there's still quite a lot of unknowns here. There's a lot of optimization that you can do to arrive at a sort of best solution. In our thinking, it's leading to a kind of full intake on the front of your spacecraft, which might, in order to basically maximize the area you're collecting propellant from. And then the instinctive solution is to have solar panels angled into the flow. So then you might think of something like a sun synchronous dawn-dusk orbit. because that's actually when you are aligned with the sun for maximum periods of time, so that you're maximizing the power you're gaining from your solar panels while orbiting the Earth. So your orbit is basically processing as the Earth moves around the sun, while also that allows you to angle the solar panel like into the flow, so parallel to the flow direction. That's the more aerodynamic arrangement. What complicates things a little bit is that the drag tends to be a different type of drag than what we experience, what we're used to at sea level, like here. It's more about individual particles and the integration of like all of those collisions with the spacecraft than it is about kind of fluid effects of the air behaving like as a continuum. So that's why you wouldn't get lift. That's like a question I often get. It's like, okay, cool, we get drag, but that's great because we can still get lift, right? Actually, in this regime, it doesn't really work that way, because this is called like the free molecular regime. So that's once your particles are rarefied enough. Like a nice explanation of it, I think, is basically the particles are so far apart. If one particle hits your spacecraft, it basically is very unlikely to collide with any other particle. That's why you don't get these fluid like continuum effects. The air is basically operating in kind of a different regime. So that's the analysis we find. What we find also, like kind of the big takeaway from our mission analysis, is it's the specific impulse that's really important, less actually the thrust to power. So it's basically all about like minimizing the area of those solar arrays, even if they're exposed kind of angled to the flow. That actually, in our opinion, still generates quite a lot of drag according to our models. But here we come more into also like what kind of materials you might want to use. So we are assuming quite traditional material properties. If you're able to manufacture materials that have, let's say like better reflection properties for these air particles hitting it, that might go a long way to sort of like easing the requirements on the thruster.
So less like a whale shark in that you're not getting that aerodynamic effect. And so when you say that you're trying to maximize, so essentially it's about accelerating the particles as fast as possible with the most powerful electric field that you can generate from the solar panels that are small enough as possible, so that you don't generate too much drag as your spacecraft is sort of walking along that knife edge as we talked about.
Precisely. And it's maybe about putting some of your payload, sorry for interrupting, or some of your like components, right, what you really want to be launching up there, actually in sort of the shadow of the intake. So that is what we were kind of talking about before, of like, it might change the way you configure your spacecraft. It might change the way the spacecraft looks, because you obviously don't want like a huge sensor or a camera or something sticking out into the flow, because that's actually generating drag. So you want to be sort of hiding them behind maybe a kind of like a frontal intake that is occupying, then maximizing the collection area.
Now, does this scale up and down to various sizes? Could you have versions of this that are just a few kilograms, and could you have versions that are tens of thousands of kilograms? Do you think there's because with the larger ones you get more momentum, right? But also a larger surface area. So which way do you think this is going to go?
Yeah. So if you allow me, I might answer in like two parts this one. First of all, it definitely scales, but like a limiting factor here might actually be our ion thrusters, our ion engines. With plasma physics in general, it's usually much easier to get the properties you want at higher powers. It's normally easier to couple power into a plasma at higher powers, i.e. larger solar arrays, i.e. a larger spacecraft, like maybe in the kilowatt range, right? Maybe we're talking a little more sort of like geostationary orbit satellites, this kind of power range, right? What you'll see like in general in electric propulsion at the moment, a lot of people trying to miniaturize to like CubeSat size, what you're saying, a couple of kilograms maybe. That tends to be quite tricky to gain the same power efficiency, because you don't have so much power to play with. So that's kind of a limiting factor. It'll be easier to have high enough fuel efficiency of your ion thruster at like the kilowatt level than it will be at the 100-watt level.
But you were saying like geosynchronous, like several thousand kilogram satellites are probably most efficient compared to the smaller ones.
Balance. And actually, sorry, what you were saying is a good point. That like it will come back to a little bit of a control problem. So imagine you have a thruster with a certain capability. It can generate like, let's say 10 million newtons of thrust. Then, as you were saying, if you have a heavier spacecraft, that gives you a lower or like also let's say like a higher ballistic coefficient, so it'll stay in orbit longer, right? It has less tendency to re-enter for its given area, like drag area. But at the same time, you actually want your thruster to be able to move your spacecraft. So there kind of tends, what we found in some of our analysis is there tends to be like a Goldilocks zone or a sweet spot between thruster size and then also mass of the spacecraft too. So like this all is coming into play, right? As you were saying, like a heavier spacecraft will remain in the orbit for longer. Like re-entry will take a bit longer because it has a higher ballistic coefficient, basically.
Now, one of the things we know is that the atmosphere isn't this completely stable thing, that solar weather can change the shape of the atmosphere. What effect do you expect that would have on a satellite that's at that altitude?
Yeah, this is a really nice point. It has quite a large effect, actually. Normally, in periods of higher solar activity, the denser layers of the atmosphere that are kind of normally lower are shifting outwards. So that means that usually the air you're flying through is actually more dense at a certain orbital altitude. So what we expect in this kind of problem is that higher solar activity tends to make it trickier, tends to make it harder to achieve this drag compensation, right? The balance between thrust and drag that we are looking for. However, it's also a case of adapting to it. So let's say the atmospheric density is shifting to higher periods. What that might mean is that your spacecraft will just orbit a little higher, basically. And it would like then you would want to develop a control system that is basically targeting like a constant density. So you adapt to the solar conditions accordingly. Often though here, like you might want a really precise, really stable, really circular orbit as spacecraft tend to want to operate in, right, without moving around all the time. So here maybe there's a bit of a challenge or a compromise, because like for instance, I think reasonably recently there was a loss of like a batch of Starlink satellites which encountered higher solar activity than maybe was expected, therefore higher drag, and therefore their ion engines weren't actually able to like raise the orbit fast enough. Yeah, so these sort of concerns. That's like quite a nice example, I guess, of it.
But it is interesting, like at least you have that capability. You have unlimited capability to change your orbit as necessary to adapt to whatever the conditions are. And you might learn, oh, there's a solar storm coming. We've got 8 minutes or 24 hours to start raising the orbit before the actual solar storm hits. And then we can drop back down and we can change direction. I mean, do you imagine that they could actually change their orbits? Like say you start off in one orbit, but over time you could start to shift, which parts of the Earth you're orbiting overhead?
So unfortunately, as we mentioned before, it's your fuel source is actually tied to the orbit you're flying through. So it's a little more like you might want to adapt to the conditions rather than being able to like a priori say I want to go there or there, because then the atmosphere just won't be dense enough for you to generate like a dense enough kind of flow of neutral particles that you can ionize, that you can turn into a plasma. So that actually in the analysis I've done has tended to be the limit. Like why it's beneficial to fly higher, let's say even like 300 kilometers, because obviously you have less drag, but it's just about getting enough density into the thruster of air particles. So if we can move towards being able to operate at lower densities, so these numbers might not mean much to most people, but let's say more like 10 to the 17 neutral particles at inlet, that kind of order, whereas electric propulsion systems tend to operate more like 10 to the 18, 10 to the 20, 10 to the 21 particles per meter cubed. If we can reduce the density, that would really help. One idea that people are thinking of is actually bringing a small tank on board. This is like a little kind of bit of a compromise, because we want to ideally not have to take any propellant with us. That's the key, like the main advantage of this, right? But it might be quite beneficial to bring like a small tank of xenon with you. So in certain periods, you have that capability to say, okay, we really need thrust now. We're going to use a bit, and it's going to be disproportionately like useful or beneficial to us.
Right. But because you're, again, walking that knife edge, every kilogram matters.
Yeah.
So then let's talk about the advantages of this. You mentioned the altitude. So you're looking at potentially having satellites orbit at 200 kilometers ish above the Earth. And as you said, that's half the height of the International Space Station. That is much lower than existing satellite constellations. What are some benefits that you get from orbiting that low?
So the benefits, like broadly, might be kind of in three different groups. So the first perhaps might be for like science missions. So a good example, actually one of the few spacecraft that has flown in these orbits, like we are calling them Very Low Earth Orbit or VLEO, is the ESA Gotcha mission. So this was a gravity mapper, so looking at really high like resolution mapping of the Earth's gravity field. Which, I mean, often the Earth is approximated as a sphere, but it's really not, right? So kind of the non-sphericity of the Earth's gravity. This is something you can learn from these orbits, and then you can obviously project that to other fields. So you can learn more about the magnetic field. You can learn more about like ionospheric conditions in the upper atmosphere. So that might feed into our climate models. That might feed into better understanding, right, of the kind of like of the behavior of the Earth. So I think that's very exciting. The other category might be for Earth observation, so imaging the surface of the Earth. Again, unlike maybe the second spacecraft that has flown in these orbits, of the two is like a JAXA mission called Tsubame or SLATS. So this was like with the same imager. It started at 400 kilometers and it was imaging like a junction in Tokyo. And so you have a certain resolution, let's say it's a couple of meters. And then at the end of the mission, it was descending down to 200 kilometers and taking that same photo of the same junction in Tokyo. I mean, if I'm getting the city right. So, and you can really see the difference with the same imager in resolution and how much better that is at a lower orbit. This is related to something like even the Rayleigh criterion. If just physically, the distance you are from your target, either you can get a much better resolution or you can get a smaller aperture size for your imager, for your camera. Either way, I mean, that's beneficial. The third kind of group of advantages might be for a communication satellite or a constellation, something like Starlink. So if you're providing internet or connectivity to users on ground, having the spacecraft physically closer should give you much better latency. So like a faster connection to the user on ground because there's physically less distance for the signal to cover.
And it's interesting, people then are going to have some instinctual responses to this. Satellites at only 200 kilometers altitude. What about the space junk?
Mm-hmm.
What about the space junk?
So this is actually, in theory at least, a very nice advantage because space junk shouldn't be a problem. So we have examples of spacecraft in these very low Earth orbits where the propulsion system has stopped operating and they've re-entered in about 3 weeks. Depends a little on the mass of the spacecraft. But effectively, once you switch your engine off or once your engine stops working, I mean, the satellite is not going to stay there. It experiences quite a significant atmospheric drag. So therefore, it brings it down like naturally. Of course, like I think in space in general, we should focus more on demisability studies. We should make sure that what is re-entering Earth is actually all going to burn up in the atmosphere. I think this is very important. But in general, for these kind of air-breathing, very low Earth orbit applications, that's actually a huge advantage that you don't pose any risk of leaving junk, of leaving space debris.
And it's like the higher the altitude, the bigger the space junk problem is. The stuff that is at, say, the International Space Station, you're looking at a couple of years, but the stuff that's at 1,000 kilometers altitude could be there for hundreds of years. And the stuff that's even higher could be there for tens of thousands of years. Like it's never going to go away. And the stuff at geosynchronous is effectively there forever. Mm. And so really, you want this stuff to be cleaning itself up. And so there is no space junk at 200 kilometers altitude. It all burns up. It all goes away.
Precisely. I mean, people talk about having like drag sails for spacecraft, right? Like, or kind of making deorbit maneuvers where you're deliberately going to a lower altitude such that that at 200 kilometers, you'll burn up in a few weeks. So that kind of solves the junk problem.
And then the other issue that I'm sure people are concerned about is the light pollution from low altitude satellites. So how do they generate light pollution?
I think often, I mean, I'm not an expert in this, but I think often it's been a case of reflecting sunlight. I'm pretty sure that Starlink, for instance, has undergone a few iterations to make them less reflective, such that they're not, sort of causing these lines of satellites or of dots on like astronomical observations, telescopes on Earth, this sort of thing. So I think that's a really important direction to go in. Just purely making your spacecraft less reflective. Especially this can be, I guess, if you're using large solar arrays. Perhaps one solution is to kind of like mount as many of the solar panels on the body of the spacecraft rather than having huge arrays sticking out into the flow. And that's actually also beneficial from this drag problem, right, that we've been discussing. You don't really want to have big things sticking out into the flow because that's generating
But isn't the
drag.
problem like the problem with Starlinks is that they're only they only cause light pollution when they're in sunlight, but the observer is in darkness. So you only get that in the initial couple of hours after sunset, before sunrise, at high latitudes when you're attempting to make your astronomical observations. Once the satellite passes into shadow, then it's effectively invisible again. And so wouldn't a satellite that is much lower altitude pass into shadow a lot more rapidly than one that's at a higher elevation? So won't the light pollution problem actually be significantly less because these things are in shadow almost immediately once they, once it's nighttime?
Yeah. I think that's an excellent point. I also think you're right, just based on your on your explanation. Um,
Yeah.
yeah, I think maybe there's a little bit of a consideration involved, right? And also like which orbits can we use such that we maximize both the sort of availability of power and of air particles, and then also minimize disturbance to people on ground from reflections. So I'm sure like there can be kind of like a good trade-off found between those two as well.
Yeah, I mean, it'd be interesting to hear somebody actually do the math on this, but my
Mm.
guess is that you'll find the actual disturbance will be lower than it would be for a higher altitude. In Canada here, I can watch the International Space Station pass overhead for its entire flight because I'm far enough north that
Mhm.
sunlight is peeking over the top of the Earth and illuminating the station. And it's at a high enough altitude that you can see it go by. But other times you see satellites, you watch them for a little while, and then they disappear because they're just passing into the shadow. And I think
Mm.
it's that shadow that is the key. It'd be interesting to sort of see what the difference is. But
Yeah,
the number
totally,
that you
totally
would
agree.
require, when you look at, say, Starlinks, they're planning on building whatever 50,000 of these things, right? And
Mm.
that's to be able to provide communications at whatever 500 kilometers altitude. If you're much
Mhm.
lower, will you need more of them to provide, say, communications coverage?
You would, yeah. So the coverage is reduced. So I think, like again, this goes beyond my area of expertise, but I've heard people much smarter than I am talk about perhaps like multiple shells of constellations. So you might have the higher shells at higher altitudes to basically give you that coverage to maximize, which bits of the Earth you have access to, and then you might have lower shells, for instance, something like an air-breathing, very low Earth orbit constellation, which might give you that like really kind of reduced latency, right, in your connection. So that kind of really high speed element of it that might not be available all the time. You might, because it's not feasible probably to create that many spacecraft at such lower altitudes that you would need for full coverage. So it might be about kind of optimizing the different orbital regimes to what they're best suited for.
So, practically speaking, what are the plans for various groups around the world to actually build like, is anyone working on a prototype right now?
Yeah, the kind of state of the art at the moment is to assemble this system and test it on ground on Earth in a sort of environment representative of very low Earth orbit. This is quite hard to do because to replicate the sort of conditions to have a sort of wind tunnel for 200 kilometers is quite tricky. A really kind of like fun idea that people have had and have used so far is to actually put an ion engine upstream in the vacuum chamber and then have the exhaust of that firing on air as actually like the wind tunnel that you would test your intake and your thruster in. So, like a nice example of this was done a few years ago, about 2018, by Citile. So this is a company in Italy, and these are some of the like our colleagues that we've worked on as part of my PhD, and that was like kind of one of these first fully integrated tests. So they managed to generate, I think, if I'm getting it correct, something like 20 millinewtons of drag and something like 6 or 7 millinewtons of thrust. So more drag than thrust, unfortunately, at that stage. But that was quite an unoptimized, very first order system, and just like to check the concept. It's that level of study that I think most groups around the world are at the moment, is like coupling this whole system together in a vacuum chamber that's big enough, and kind of trying to do as good of a job as possible of recreating very low Earth orbit by having a thruster firing on oxygen and nitrogen upstream.
Right, right. So like one ion engine is firing on another one to provide the particles at high speed.
Precisely,
That's
to
really
kind
interesting.
of, because you want flow at about 8 kilometers per second. That replicates your orbital velocity in these types of orbits. So that's kind of the conditions, and you want your densities, as I mentioned, something like the onset flow density to also match the number of particles that the intake is seeing. And then you want to see whether your intake collects them, how well your thruster ionizes them, accelerates them, and therefore, like, what overall is your balance between drag and thrust.
Right, right. So we're still a couple of years before somebody tries to launch a test satellite or have a instrument on board some test satellite to see how well it's going to actually work in the conditions of space.
We are, yeah. I think hopefully in the next few years it should be possible. There are like research groups at universities, and I think even a few startups and companies that are planning to do it at least. It's kind of maybe like a new problem, because almost the whole spacecraft has to be designed around the propulsion system, or the propulsion system is so integral. It's not a case of like, oh, we'll launch a spacecraft that we know works really well, a very like sort of safe platform, and then we'll just put a small thruster on it and see how it works, which often is already like quite challenging to do in electric propulsion. Here it's like, you really have to think about the whole spacecraft, where is your intake sort of, and kind of, we're not generating too much drag, and then having sensors on board as well to see how your thruster is working. Yeah.
To an altitude that nobody wants to go to.
Yeah.
Right.
Although the initial orbit is a bit easier, right? Because like I think even Starlinks get deployed at something like 200 kilometers. So you don't have to expand so much effort to sort of get your spacecraft to a very high orbit initially. Like the sort of like
Right.
deployment orbit is enough.
But okay, yeah. So then I'm sure you've thought about other places in the solar system, and you have different numbers, you have different kinds of atmospheres, you have different levels of gravity, you have different distances from the sun to provide available amounts of electricity. Have you thought about other places that an air breathing ion thruster might work?
Yes, exactly. Or atmosphere breathing, at least, right? I don't know if
Atmosphere
air is
breathing,
called,
yeah,
like,
it's
is it
not
called
air,
air
yeah,
if it's on Mars or if it's on Titan? I don't know.
yeah, yeah.
Yeah. So yes, definitely. And there's been like really exciting, really fun studies in the literature on this as well. I think a prime candidate is Mars. Although your thruster would have to adjust from operating primarily on oxygen or nitrogen species, I guess more towards CO2, for instance, perhaps some methane as well, but these kind of gases. I think another candidate would be the atmosphere of Titan as well, for instance. And here we get to like even a fun overlap with things like Ingenuity, right? So using more traditional like aerodynamics, rotorcraft, for instance, for helping to explore, kind of these other places in the solar system. But yeah, the air breathing thing also works there. It's just, as you say, it would be at a different altitude, because this balance between available atmospheric gas, and power, and gravity, as you say, kind of comes in a different place. But from our early studies, like it should also be feasible on Mars, just at different altitudes, basically.
But you've got 1/4 the energy density coming at you from the sun.
Mm-hmm.
Venus feels like it would be even better because you've got even more solar energy coming at you,
Mm-hmm.
and yet the
Yeah,
same gravity as Earth.
yeah, perhaps the problem might be like the composition of gases. I'm not an expert, but maybe there's some pretty nasty gases in the Venetian atmosphere. Stuff like sulfuric acid, perhaps, might not be too easy to deal with. But then neither is atomic oxygen. So this is one of the things on Earth. Actually, at these orbits, you get a lot of dissociation of the molecular oxygen just into monatomic oxygen, into oxygen atoms, which are also usually pretty corrosive to spacecraft. And one of the reasons why spacecraft don't typically operate in these orbits, in these altitudes. So it's also then a big facet of it is the materials problem. So I think we can get a lot of advantages by developing better materials and materials better suited to sort of operating with like a highly reactive monotonic oxygen population. Like even if that's like half of the airflow you're seeing, for instance, it's large fractions basically. And the other problem is that varies over time. So based on the solar conditions, that actually and where you're flying, like which latitudes you're flying over, that will affect actually the composition of gas as well. So you have to have some flexibility to whether you're seeing like mostly nitrogen molecules or, for instance, mostly oxygen atoms.
Now, this only works when you are in orbit around a planet close enough that you're able to actually draw in oxygen because or draw in some kind of atmospheric gas because you're attempting to fight against the gravity and you're trying to achieve that balance in your orbit. But once you're away from a gravity well, is there like enough gas density just in the solar system, maybe from the solar wind, things like that, that you could draw upon that to provide any kind of thrust when you're away from a planet? You're in solar orbit instead of maybe planetary orbit.
That's a really interesting idea, actually. We personally haven't explored that. I'm not sure I would be, knowledgeable enough to actually say anything on that. Definitely, already at Earth, though, you're pushing the boundaries of like the minimum density of particles you need to actually ignite a plasma in where we tend to operate electric propulsion devices at, like ion engines. So just like instinctively, I would say it would be quite hard to get enough particles in to actually generate your plasma. But there might be much, sort of more intelligent ways of doing it, such that you can work at lower densities.
And then now we're going to go right into science fiction for one brief moment. And that is there's this classic idea of traveling to other star systems with the Bussard ramjet, where you are traveling at high velocity. You've got this gigantic magnetic scoop that's drawing in particles of hydrogen and other stuff. And then you are using them to generate fusion to blast out the back. And you're living off the land, as it were, traveling between stars. And it feels very familiar. This idea of using an atmospheric breathing ion engine feels very similar to that. But I know recent studies have said, oh, you would need a magnetic field that is like 1 astronomical unit long to be able to actually draw in enough particles to be able to fire up your ramjet. And we can't make a magnetic field that is an astronomical unit long. So, I mean, do you think at all about interstellar applications to any of this kind of technology?
I or sort of like the majority of the research groups working on this, I don't think have so far, but it's definitely a very fun idea and one that's definitely worth exploring, right? Like every idea is science fiction at some point. So absolutely, I think it's a nice one to explore. I suppose though that it would be the problem of what you're saying. So just having your scoop, whether that's magnetic, whether that's passive, whether that's active, because for instance, even in this case of the air breathing at Earth, people have talked about, not just like a passive ramjet intake, but actually one that's actively pumping the air in, like sacrificing a little bit of power to generate a pump, like almost like a turbine molecular pump that you use in vacuum chambers to actually increase that density. So yeah, I think the problem might be more just collecting enough matter.
Yeah. I mean, people just don't understand how not dense interstellar space is. I mean, you could count the number of particles, by hand within a cubic meter of space. There's not a lot of atoms there to be found. Well, Mansur, what are you obsessed with right now?
What am I obsessed with right now? I think
Yeah.
I'm still pretty into the air breathing topic. I mean, I think it's very natural once you've just done a PhD on it to sort of want to
Yeah.
continue. Like I think there's plenty of kind of meat to get into it as well. So that there's like so many facets of this problem to solve, and I think it's a very fun challenge. Like it being on a knife edge is maybe from a research perspective, I think that's really fun, right?
And I mean, is there a part of it that you think more about than others?
I mean, I'm an aerospace engineer, and propulsion has always been the sort of the draw for me. So I'm definitely more on that side of things. The thing is that with electric propulsion devices with ion engines, it's been very much optimized for xenon for the last couple of years. Actually, like early on in the history, it started more, I think, with mercury or cesium, these kind of propellants. So things that are really heavy and very easy to ionize. And then kind of as time has progressed, it's moved more towards xenon, maybe argon, krypton even, if we're talking like the latest Starling, of basically noble gases that are inert and unreactive and easy to store. So I think there's a big jump or step to kind of now really optimize thrusters for other propellants such as air. And not just like, oh, we have the xenon thruster and we're going to see how well it works with air. It's of actually like optimizing and really looking at the, how does ionization occur, right? How do we like more efficiently couple energy into the plasma for these type of molecular gases, molecular species? And how do we minimize the energy lost in things like dissociation? So breaking the molecules up into atoms, or like exciting molecules rather than ionizing them specifically, right? So exciting like vibrational or rotational modes inside the molecules. I think that's like a very fun problem, and that like is a really interesting research direction. So that's primarily where I'm coming to it from.
You're just going to have to get a second PhD in plasma physics to really understand it, which I hear is easy. It's one of the easier degrees to get is plasma physics. So that should be a good challenge for you. Well, Mansur, thank you so much for taking the time to chat with me today, and good luck with your research. And I hope one day we see an air-breathing ion engine flying overhead.
Yeah, thank you very much, Fraser. I hope so too.
I hope you enjoyed this interview with Dr. Mansur Tisaev. I'm going to give you some thoughts in a second, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew Gross, David Gilton, and David Matz, Dennis Alberti, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Modso, Paul Rohrbach, Stephen Krasaki, Stephen Filemonley, and Vlad Chiplin, who support us at the Master of the Universe level, and all of our other supporters on Patreon. As you probably get, I'm pretty excited about this technology, this idea that you could have a satellite that requires no power source. It doesn't have to have a nuclear reactor on board. It's just using solar power from the sun. And it doesn't need to have a propellant on board. It's pulling in all of its propellant from the air and able to maintain its orbit. And in theory, this thing could just fly forever, performing whatever functions it needs to do. Now, the requirement, of course, is that it has to be in orbit around some planet with an atmosphere, but there's a plenty of those, and they're scientifically interesting, whether it's Venus, Earth, Mars, Titan, maybe some of the gas planets, who knows what's possible. And so I'm really excited for this technology. At the same time, though, it appears to be one of those technologies that's like right on the knife edge of what is possible. That you've got to have things perfectly in balance to be able to overcome that drag, to be able to generate that thrust. And just by definition, it's always going to be in this sort of perfectly balanced state. So there's a lot of interesting technology problems that need to be solved, but it seems feasible. So who knows? One day we could have satellites that are flying overhead that are in perfect balance, requiring neither electricity nor propellant to maintain their altitude. All right, we'll see you next time.